Good morning, everyone. So up until now, we started with doing derivatives the long way. And that's a very, very important process. Then, last time we had joyfully seen there are some very simple rules. Today we realize some of the rules are starting to get more complicated. And we're going to introduce two new rules today, as you can tell by the title, the product and the quotient rules. And then we're going to talk about higher order derivatives. This lesson, I suspect, may creep into, we're going to probably need 2 days for this. So we'll get started. But let's open it up with questions on the 3.2 assignment. Good morning, Sarah. So at the moment, we're just checking in. Are there any questions on 3.2? And you can, once again, use the chat. You can send me a message directly, text message. All right, then we're going to get going on, let's see, we can hide these. We're going to get going on the product and the quotient rule, higher order derivatives. As you can see, we're going to try to do 4 things today. Find the derivative of a function using the product rule. Secondly, find the derivative of a function using the quotient rule. And third, find the derivative of a trigonometric function. And maybe at a later time, we will, I think we're going to run out of time, but we're going to talk about find a higher order derivative of a function. Okay, so let's get into the product rule. So, like I said, up until now, you've had the ability, to just use simple rules, and they all made sense. There are times when those rules do not suffice. Sometimes you just have to deal with them as the product of 2 separate functions. And that's what this rule is for, the product rule. It says if you want to take the derivative of the product of 2 functions, f and g, take the first times the derivative of the second plus the second times the derivative of the first. So I'll just repeat that. The first times the derivative of the second plus the second times the derivative of the first. So let's take a look at, now I will just tell you, in this example, we could have actually, we didn't have to use the product rule. We could have multiplied this thing out first and then just used the rules that you learned yesterday. But we're using it as an example because there will be times when you have to use the product rule. So let's just ease into this. So here's our function up here on the top. 3x minus 2x squared multiplied by 5 plus 4x. So we want to take the derivative of h of x. So we start by taking the first times the derivative of the second. Good morning, Rachel. Plus the second times the derivative of the first. Now, by the way, you haven't seen this, but this d dx is a way of saying the derivative of. So this reads again, the first times the derivative of the second. We actually haven't done anything yet. We're just saying times the derivative of the second plus the second times the derivative of the first. So this is another, this turns out to be useful notation for an example like this. Now let's actually do it. The first times the derivative of 5 plus 4x. And the derivative of 5 plus 4x, well, the derivative of 5 is 0, constant, and 4x is 4. So there's your derivative. Let's open up the pen here. So there's, the derivative of the second, plus the second, 5 plus 4x, times the derivative of 3x minus 2x squared. Derivative of 3x is 3. The derivative of negative 2x squared is minus 4x. Okay, we've executed the product rule. Now it's just a matter of algebra to bring things together. So we take 3x minus 2x squared times 4, and we multiply 5 plus 4x. So times 3 minus 4x. 5 times 3 is 15. 5 times negative 4x is negative 20x, and then 4x times 3 is a plus 12x. Well, negative 20x and a plus 12x turn out to be, I guess you could say they skipped a step. And then lastly, 4x times negative 4x, negative 16x squared, and then just add like terms. So there's our first taste of the product rule. All right. So let me just ask, is there any questions so far? So now we're going to take one that you have to use the product for. There is just you can't use any of those rules we learned the other day. They're not sufficient. So if you look at the function here, well, x times e to the x, the only way we can do that is with the product rule. The first is x, the second is e to the x. They're multiplied, so we use the product rule. So here we go. The first, x, times the derivative of e to the x, plus the second, e to the x, times the derivative of x. All right, what is the derivative of e to the x? Well, that's from yesterday. That's awesome. That's e to the x. Plus the second, e to the x, times the derivative of x. The derivative of x is 1. And if you want, you could factor out, factor out the e to the x. Either one of these is actually correct, I mean, this top one could be stated this way. You could say x e to the x plus e to the x. You don't have to have the times 1 there. And then, yes, you could factor out the e to the x, which they seem to like to do. So there, we've executed the product rule. Let me know if you have anything you want to stop me on. So let's do this one now. Example 3. So what's the derivative of 2x cosine x minus 2? So we've got kind of a combination of rules here. As you look at this first term, we have the product of two things, 2x times cosine x. We need to do the product rule on that part. So here, and this is just a separate, this thing on the end, minus 2 sine x, that's just the constant multiple rule. So, but first, let's handle this product, 2x times the cosine of x. So the first, 2x, times the derivative of the second, plus the second times the derivative of the first. And then, all right, the constant multiple rule says you can pull the constant out and negative 2, and multiply it by the derivative of the sine. So, okay, finishing the product rule. 2x times the derivative of the cosine. The cosine derivative is minus the sine x plus the second cosine x times the derivative of 2x. 2. All right, and then let's do this last one. Minus 2, derivative of the sine is the cosine. Well, all right, so what's 2x times minus sine x? Minus 2x sine x. And then these two terms wipe each other out. You get 2 cosine x minus 2 cosine x. Final answer, negative 2x sine x. So now you've seen two examples that have to be done. I mean, you can't avoid the product rule. So right off the bat, you should learn this rule. You've got to memorize this, okay? So to take the derivative of product, take the first times the derivative of the second plus the second times the derivative of the first. All right. So it's time for the quotient rule. So let's make this a little bit bigger. So now what happens if you have the quotient of two functions? F of x over g of x. Well, obviously g of x can't be 0 because it's in the denominator and you can't handle a 0 in the denominator. So, I mean, that's pointed out up here in the top. Okay, we already know that can't be. But, so here it is. And here's the rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So, yeah, I know, it's getting a little more complicated. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. All right, and sorry, there's no shorter way of doing that. That's it. Okay, let's make use of it. I know that, by the way, the notation maybe gets in the way a little bit, but if you remember those words, and they've got it, you know, they've got it outlined right there for you. So if you remember the words, you need to learn this right away. You guys got to pounce on this right away. You need to know these two new rules. Okay, now using the quotient rule. So let's take a look at this example 4. Example 4 in the book. Okay, so we have the quotient of two things, 5x minus 2 over x squared plus 1. Now, in the past, we relied on algebra to bail us out. You know, like, can we factor? Can we use the Can we use the conjugate rule? Can we do some algebra thing to get that simplified? And the answer is no. So here we have to use the quotient rule. All right. So let's apply it. The denominator, x squared plus 1, times the derivative of the numerator, minus the numerator, 5x minus 2, times the derivative of the denominator, all over the denominator squared. All right. By the way, don't worry about that denominator squared. We're not going to touch that. We're going to just leave it as squared. So now you actually execute it. X squared times, what's the denominator of 5x minus 2? Yeah, it's 5. Minus 5x minus 2 times the derivative of x squared plus 1. 2x. Okay. Well, let's just multiply it out. 5x squared plus 5 minus 10x squared minus 4x in parentheses. Bring the numerator all together. and you've got the derivative. Okay, any questions? Quotient rule. Now, as usual, one has to be on top of their algebra game to really be effective using these rules. And this next slide indicates that often it's best to rewrite before you actually take the derivative. So here you can see, well, we got a problem here up in the top. 3 minus 1 over x plus 5, and you're supposed to find the equation of the tangent line at negative 1, 1. So the problem is this 3 minus 1 over x is not, I need to bring that together. Otherwise, I have half a fraction on the top, and that's over another fraction. So you'll see here, using algebra, we had to do something about this 3 minus 1 over x. So what they did is multiplied the top and the bottom by x. Legal, because if you multiply top and bottom by the same thing, you're multiplying by 1. So we might have handled that by getting a common denominator on the top, but this is a valid way. And then when you multiply x times 3, you get 3. X times negative 1 over x is, thankfully, no more fraction, negative 1. On the bottom, we also have to multiply x times x plus 5. All right, so now, using algebra, now we can execute the quotient rule. So now we pull out the quotient rule and say, denominator times derivative of numerator minus numerator times derivative of denominator. Multiply it out. 3x squared plus 15x minus 6x squared. And then, anyway, then you bring it all, you finally solve for simplifying, getting the like terms together on the top. And here is your general derivative. So that, that's the f prime of x. All right, now we can go back at this point. What's the derivative at negative 1? And all you do is plug in negative 1, whack away at it. Let's see, that would be what? Negative 1 squared is positive 1. Negative 3 times 1 is negative 3. 2 times negative 1 is negative 2. Negative 3 plus negative 2 is negative 6. And negative 6 plus 5 is negative 1. All right, now we got the bottom. What's negative 1 squared is 1. And 1 minus, all right, hang on a second. Did I do the arithmetic right there? So on the bottom, you have negative 1 squared is 1. And 1 minus 5 is negative 4. And negative 4 squared, what am I doing wrong? So let's try that one more time. On top, negative 1 squared is 1. 1 times negative 3 is negative 3. Negative 1 times 2 is negative 5. Oh, negative 5 plus 5 is 0. And then on the bottom, you get 16. But 0 over anything is 0. So now we found that the value of the derivative at negative 1 is 0. So there's the slope of our tangent line. And so now they talk about the point slope form, but I would just go back to what you know with the mx plus b. Plug in your slope of 0. And now plug in your point. Negative 1. Let's see, 1. And you have 1 equals 0 plus b. So b is 1. Slope is 0. So you can write 0x plus 1 or just y equals 1. So I still recommend, instead of using the point slope form like the book does, I would use the slope intercept form. Same result. Any questions? All right. So now let's do another quotient rule here. Okay, and you notice we're going to do a little trigonometry. So, I mean, you already, this is a way of discovering what's the derivative of the tangent. Well, you can look in the front of your book, but we can actually figure it out because we know that another name for tangent is sine over cosine. And then we could use the quotient rule to find the derivative of sine over cosine. And that's what we're going to do. Denominator times derivative of numerator, the derivative of the sine is the cosine, minus numerator times derivative of denominator. Derivative of cosine is minus the sine. And what happens when you simplify all over cosine, the denominator squared? So in the top, we simplify, we get cosine squared plus sine squared. Very famous identity says cosine squared plus sine squared is 1. And sure enough, what's 1 over, so the final answer is 1 over cosine squared, which is, yeah, it's the reciprocal of the cosine is the secant. So the final, so basically what we just found is the derivative of the tangent is the secant squared. And we used the quotient rule to find it. Questions? All right, let's go to another one. Back to the book example here, derivatives of trig functions. So we have, yeah, it says, okay, so what we're supposed to do here is we've got an equation. 1 minus cosine x equals cosecant x minus cotangent x. And you're supposed, it says differentiate both. You're supposed to differentiate both forms, meaning both sides. Okay, so let's take this first one. Y equals 1 minus cosine over sine. Take the derivative using the quotient rule. Denominator, denominator, sine x times derivative of numerator. Well, what's the derivative of 1 minus cosine? The derivative of 1 is a constant, so that's nothing. And the derivative of the cosine is minus the sine. So what's the derivative of minus the cosine? Positive the sine. So all of that just to, just to get that. All right. Minus, so denominator times derivative of numerator minus numerator times derivative of denominator. Okay. So when we multiply out, sine times sine is sine squared. And when you multiply this out, you get minus the cosine plus the cosine squared. And you notice again, we have this identity, which is highlighted over there. That sine squared plus cosine squared is 1. So I can literally replace them. And you notice that I get a very similar looking derivative. I mean, this is what we were working on right here. And look at the derivative of 1 minus cosine over sine is 1 minus cosine over sine squared. Okay. So, all right, let's just, that's enough of that one. We did that already. Okay, yeah, simplifying guidelines. So this has nothing to do with derivatives now. This is saying, hey, after you're done doing your derivative, get things simplified. And this is advice from the book, so that when you look in the back, the answers most likely will be the ones that you will find there. So in example 1, they're saying, hey, after you took the derivative, if you get this, you, of course, can just do the algebra, multiply those out, and bring it together so it looks like this. Okay, so what they're saying is multiply things out and gather like terms. All right, the second one, 2x times negative sine equals, okay, so that's negative 2 sine x. And then you should recognize that, hey, these two are really opposite sides of each other and they eliminate. So again, you should do this kind of simplifying. This next one, don't mess with the x squared minus 1, the x plus 1 quantity squared on the bottom. Just let that be. Don't touch it. But on the top, multiply and bring the like terms together. Okay? Likewise on this one, example 5. Example 9, when you're doing a trig problem and you get, an identity like sine squared plus cosine squared as part of it, this is what that you need to find that, you need to know that identity and replace that. So okay, so these are just guidelines for how far should you go. Don't ever touch that denominator squared on the bottom. Just let it be squared. But with the numerator, yeah, you want to get things simplified, get them together. Okay. So now we want to have a talk about higher order derivatives. Okay, so higher order derivatives means you can take a derivative, and then you can take a derivative of the derivative, and then you can take a derivative of the derivative of the derivative. So this repeat process is called a higher order derivative. So for example, and by the way, this last column here, you can disregard, because that notation, I don't know. We just don't ever use that. But anyway, I would say we're going to be here, and we're going to mostly use this notation. You can also use this notation. So I guess you can disregard most of these, but those first two columns you got to know. So I'm not sure how useful this is, but anyway, I mean, this slide maybe isn't the best, but I guess let's go to so this first notation means the first, y prime means the first derivative, f prime of x the first derivative, y double prime, f double prime of x the second derivative. Okay, now let me show you an application of this. So here we have a problem. And we're going to learn a little bit about first and second derivatives here. So find the acceleration due to gravity. So because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott, oh yeah, and I could show you that, I actually have that video, but anyway, he drops a hammer and a feather. A hammer in one hand and a feather on the surface of the moon, and they land they fall at the same rate and they land at the same. So weight has nothing to do anyway, is what he's demonstrating. A feather and a hammer fall at the same rate on the moon. The position of the function for each of these is, and here's, S is a science way of saying distance. So, or displacement. S of t equals negative 0.81 t squared plus 2. And as you can see, it's graphed here. It's a parabola. It's still, the moon has gravity at just 1/6 the amount it is on the Earth. Okay. So S is the height in meters, and T is how many seconds the thing has been falling. What's the ratio of the Earth's gravitational force to the moon's? All right, so you first take the distance equation, and here's the key. When you take the first derivative, you get velocity. So what's the first derivative of negative 0.81 times t squared plus 2? Power rule, 2 times negative 0.81 is negative 1.62 t. 2 is a constant, nothing. And then if you take the second derivative, you get the acceleration. So this, this is important right here. This is saying, yeah, when you've got a distance function, if you take the derivative, you will have the rate of change of the distance, which happens to be velocity. And if you take the rate of change of the velocity, then you will have the acceleration. And the derivative of negative 1.62 t is negative 1.62. So how do you figure out that the first derivative is velocity? Okay, when you're taking a derivative, you're finding rate of change, right? So if your position has changed, what's the rate of change of the position? We call that speed. That's how fast your position is changing. And that is the very definition of velocity or speed. And then how fast is your speed changing? So think of it in a car. If you're in a car and if you quickly change your speed, what are you doing? You're either accelerating or decelerating. So if you hit the brake, your rate of speed is going to drastically change for the negative. If you if you floor it, your speed is going to drastically change for the positive. So just by very definition, velocity is the rate of change of where you are. Acceleration is the rate of change of your speed. So there's really no figuring. This is in the very definition of those terms, distance, speed, and acceleration. So anyway, this is where multiple derivatives turn out to be very handy. Let's see, do we have another example of this? No, I guess we're going to get it. So anybody else have a question? So if you take the distance equation, take its first derivative, that will give you the velocity or the speed. And if you take the derivative of the velocity, you will get the formula for acceleration. And you'll see a couple problems related to that. All right, let's try some problems here. So, using the product rule. So I did number 2 and number 6. So let's take a look at number 2. We have 3x minus 4 times x cubed plus 5. By the way, on this one, we could cheat. We could actually multiply that out and then take the derivative. Okay, and it looks like I cheated here. No, I didn't. So I'll show you what I mean by this. So on this one, we could have avoided the product rule here And we could have just multiplied 3x minus 4 times x cubed plus 5 using FOIL. And then we could have just used the simple rules for finding the derivative. But, of course, then we would have violated the directions. It says, go ahead, I want you to use the product rule. All right, so here I am using the product rule. The first times the derivative of the second, the derivative of x cubed plus 5 is 3x squared, plus the second, x plus 5, times the derivative of the first. The derivative of 3x minus 4 is 3. And then just do some, multiply it out and bring the like terms together. So there's a real simple example of using the product rule. Okay, let's take a look at number 6. The square root of x times the sine of x. We could write that like this. That's x to the 1/2 times the sine of x. So I'm trying to anticipate, hey, that'll make it easier to take a derivative if you change the square root into a power. All right, now come down here and let's use the product rule. The first times the derivative of the second, the derivative of the sine is the cosine, plus the second times the derivative of the first. Now, let me, all right, if you look up here on the top, it shows what I did. What's the derivative of x to the 1/2 power? Power rule, 1/2 x, and then reduce the power, negative 1/2. Isn't that the same as that? So that's, it's a little detached, but that green up there on the top is where I got the 1/2 times the square root of x. Let's see if I have any other questions here. Okay, let's try the quotient rule. So these are, again, this is right from the assignment. So I work on number 8. Okay, number 8, 3t squared minus 1 over 2t plus 5. Quotient rule says take denominator times the derivative of the numerator, minus 6t, plus 6t, minus the numerator times the derivative of the denominator, all over the denominator squared. Then just do simple algebra 1 to multiply and bring like terms together, and you finally arrive at the derivative. Okay. Anybody taking notes might want to grab onto that. I don't know. Do you have any questions? Don't want to buzz by you here? I guess you can always stop the video. All right. So here's another example where we have to use the quotient rule. The cosine of t over t cubed. All right. Quotient rule says take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. T cubed squared is t to the 6th. So I just multiplied things. Yeah, so here's an interesting comment. So up until, up to this point, I think you can see what I did, right? Can everybody see what I did up to the red line? Just checking my messages. Okay, previously there was a problem where the derivative of 4x was equal to 4x. I don't get that. Previously. So somewhere up above here? All right, let me see. Well, let's finish this one first. All right, anyway, does everybody see how I got to the red line? I mean, I haven't done, all I did was execute the quotient rule, and then I just did a little, I just rewrote this as a multiplication. All right. You might think that's as good as you can do, but do you notice that if I factor out, and t squared is the best thing I can factor out, if I factor it out, this t squared can cancel with the t to the sixth. So I gain a little bit. Then if you cancel t squared times t to the sixth, it's gone on the top, and you have a t to the fourth on the bottom. So now, so here's a case where algebra technique allowed me to simplify a bit further. So now I got to try to trace down this question. Previously, there was a problem where the derivative of 4x was equal to 4x. Wow. Well, I don't know where you are. Wish you could give me a few more hints on that one. There's more to my question. I know, I'm looking at the whole thing. Okay, let me try. Yeah, what you say is correct. I just don't know where, I don't get where we talked about a 4x. I'm going to have to trace that one down, okay? Thank you for your follow-up message. Somewhere in the beginning. Okay, I'll tell you what, after the video, after we're done, I will try to locate that, and I will follow up with you, okay? Something about a derivative of a 4x should not be 4x. I would agree with that. So I'm not sure when, yeah. Okay, so I will follow up after the video. All right, now, here is just, there's a section on the assignment that looks like this. It says in exercises 21 to 26, complete the table to find the derivative of the function without using the quotient rule. So they're saying do something algebraically to avoid using the quotient rule. So just take a look at 22. All right, 22. Is there a way you could rewrite this? Sure. Couldn't I just write this as 1/4 times 5x squared minus 3? And now let's see. Yeah. Do you get the differentiation? This is now a product rule, correct? So 1/4 times, so the first times the derivative of the second, first 1/4 times the derivative of 5x squared minus 3 is 10x, plus the second times the derivative of the first. Well, what's the derivative of the first? Constant, 0. So I didn't even write it down. So in other words, plus 5x squared minus 3 times 0. And I didn't even write it down. And then, of course, you can simplify this to 5x over 2. This one here. So we can pull the 6/7 out, and we can write x squared in the denominator as x to the negative 2. Now use the product rule. So we're avoiding. So what we've done is avoided using the quotient rule in this case. Does that mean you have to do it that way? No, but we're trying to teach you efficient ways to take a derivative. So the first times the derivative of the second, negative 2 times x, lower the power by 1, plus the second times the derivative of the first. The derivative of the first is 0 again, so I didn't even write that term down. And then Just bring it together. You know how the book doesn't like to have negative exponents. 6 times negative 2 is negative 12. And the x to the negative 3 goes on the bottom and becomes x to the third positive. So they're just trying to teach you good habits here. So if you can avoid using the quotient rule, go ahead and avoid it. That's okay. Or if you rather use the quotient rule, hey, you can do that too. It works. Let me just I'll tell you what, let's just illustrate that the answer comes out the same. So let's take this problem 23 and let's do it using the quotient rule. So we've got pen. Come on, pen. All right, hang on. There we go. So we've got 6 over 7x squared. All right, so now let's just come over here and we're going to do it strictly with the quotient rule. Okay, so got to get rid of that. Sorry. So let's try this again. So f prime, that's f of x. So f prime of x is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. All right, and so what does that equal to? Well, this first term is nothing. And then you get negative 6 times 14. Negative 84x over 49 x to the fourth. Okay, so now what's negative 84 over 49? Well, 7 goes into both. 7 on okay, 7 goes on the bottom. You've got 7. We wind up with x cubed on the bottom because 1 cancels with that. And then what you get on the top should be what? If you divide by 6, negative 1, 24, 14. Okay, what do we have here? 6 goes in that 1, 24, 6. Oh, okay, what did I do? I've got okay, I just got to check my multiplication here. What did I do wrong? So denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. Okay, that drops out. Negative 84x over 49x to the fourth. And then when you reduce, I'm going to have to check, but it should, I got negative 12 over 7x cubed, and here it looks like I got negative 14 over 7x cubed. Anybody see what I'm doing? Anyway, the quotient rule, I divided by 6 instead of by 7. You're right. So if you divide by 7, you get 12. Thank you. Arithmetic. And you notice we do get the same result that we got. So I mean, if you want to use the quotient rule, you're going to be fine. But it might be wise to keep in mind that you can do this algebra stuff to make things quite a bit easier. All right. Yeah, I'm going to spend just a little bit more time on this tomorrow. I've got a few more slides left to go, and I've got some more advice I'd like to give you. I see we're at 50-minute mark already. But I'm going to give you the assignment and let you get started at it. Okay? So the 3-3 assignment shown here, it's on your website, but so let's put it this way. Just get started on this. We will spend more time discussing this whole issue tomorrow. Any questions? Okay, thank you. I will see you tomorrow.